Okay, so this is a video about CMake. I've been wanting to make it now for a few weeks. Finally got round to being able to find some time to do it. So the motivation for this is if you do any kind of C or C++ programming for the Raspberry Pi Pico and the Raspberry Pi Pico 2 using Raspberry Pi's SDK, you're going to come across CMake. Of course, it's not the only place that uses it. It's used widely in many places, but that's when you're going to meet it if you're kind of a follower of this channel. So I really wanted to be able to cover the essentials of CMake for absolute beginners, because just learning a few essential ideas really helps to understand what it's about and how you use it. So this really is a beginner video. Now I'm going to start from even the simplest things of how you compile a C program, Hello World, using GCC. Then I'm going to look at Make itself. Then I'm going to look at CMake. We're going to touch on Ninja and so on. Now if some of those subjects are you already know about them, they're not something you need to learn about, I'm leaving a chapter index in the description so you can just skip forward, skip over GCC, skip over Make if that's what you need to do. But if you don't know about those things, I've got you covered as well. Okay, so if you want to find out more, please let me explain. Okay, so here is a simple C program. It just prints out Hello World. But how do you compile that? How do you convert the source code into a binary which you can run? Well, you use a compiler. In this case, we're using GCC. And so there's the command gcc-o hello w, that's the name of the binary. -o specifies the name of the resulting binary. And hello w.c, and that is this source file here. So in one command, you can convert this C program into a program that you can run. Now, if you want to, there are flags that you can add to that. For example, you can add in some optimization. Not that this program needs any, but if you wanted to in a more complicated program, you might add in -03, the third level, the highest level of optimization, and then the rest stays the same. And there are other flags that you can do as you get into more and more advanced things to do with GCC. Okay, so here we are on the command line. This is a Linux box, and as you can see, here is that simple Hello World program in hello w.c. So we do gcc-o hello w, that's the binary we want, and we want to compile hello w.c. That goes ahead, it's created it, and now we can run hello w, hello world. Simple as that. Now let's say you've got a bigger C program. Here is a C program that's going to print out 10 random numbers, but it's going to call this function called random normal. And if you notice, that's not here in this C code, but it does include something here called random.h, where random normal is actually defined. And the C code for that is in another program here, random.c, and here we see random normal distribution centered around 0. Okay, and it's using cosine and square root and log and all this stuff here. So basically this little function here is in a separate program. So now I've got two source codes that I want to use both of them to create the final program. And so here is where that function is called, and here is where it's defined. And also notice here it's including maths.h, which means we need to include the maths library, which is not part of the standard C runtime library. So the way you can compile that is like this. So this is the output name, like we had before, the binary name. And then we've got two source files, main.c and random.c. And then finally, we link against the maths library. And if you give this one command to GCC, including both C files, it will work out what to do and it will produce this final binary for you. Now there's another way to do the same thing, and that is to compile each of these files individually. So if you compile this with the -c flag, this will create main.o. If you compile this with the -c flag, this will create random.o. And then finally you can do the same thing, but now what you do is you give it the two object files, the O files, rather than the C files, and you also link against the library for maths, and that will give you the same main resulting binary. Okay, so here we are now in that random number program. There's the first file, random.c. We can also take a look at main.c, and there it is there. So to compile that, there were two ways, if you remember. gcc-o main, that's the name of the binary, main.c, and random.c, and we also need to link -l for library M, the maths library, and the compiler will sort all that out. It will compile both files, link it, and generate the file. There you go. Now we can run main, and it prints out those random numbers. The other way to do it is GCC -C main.c. That will create main.o. GCC -c for compile random.c. That will create random.o. And then GCC -o main, and we want main.o, not .c, main.o, random.o, and we also want to link against the maths library. There we go, and we can run main again, and there it is printing out those random numbers. Simple. Now, a few source code files can potentially be managed and compiled by hand, but at some point you're going to need some automation. Now, a tool like HTOP, which I feature in quite a lot of my videos, has 128 C files. It's not a particularly big project. It's sufficiently complex with 128 C, but it's not huge. But imagine trying to compile 128 C files by hand. Now, when you come to the Linux kernel, for example, there are over 20,000 C files, and that's not including the header files. So there's no way you're going to compile 20,000 files by hand. So you're going to need some form of automation. Now, one of the earliest and still most popular automation tools for building software is called Make. It was created by Stuart Feldman while he was at Bell Labs. The early version was completed in April of 1976, so decades ago, and we're still using it today. Make uses a configuration file called the Makefile to define what C files are needed and what dependencies exist between them. So here is a very simple Makefile. The core of it is here, is we're saying we want to run GCC to create hello world and compile hello w.c, just like we did before. And the way that works is that it says there's a target here. If you want to build hello w, then it depends on, this is the dependency, hello world.c. So if that changes, this command needs to be run again, and this is the command that you need to do it. By default, when you just type in make, it actually really means make all. So here for make all, we're saying, well, actually what we really mean is we want to build hello w, which means it builds this, which means it runs that command. And there's also a command here called make clean, which will just remove that binary if you wanted to have a clean start. Okay, so here is our Makefile, those three sections as we've just discussed. All you do is type make, simple as that. And as you see there, it says GCC -o hello, hello. So it does the same thing, but it did it according to the make build system. And so we can just run hello world there. We can do make clean. As I showed you, that will delete that file. So now we can do make again. Let's do make all. That's the same thing as just doing make without specifying all. And if we do make clean, again, we can do make hello w, and that will also do the same thing because it just depends on which entry point you get into that make file. So there you go, Make has built it for us using automation. Now, make files can get more and more complicated. For example, here is basically the same thing, but here we're specifying what compiler we're using, we're specifying what flags we want to use on the compiler. We specify what the source files are as a separate variable, and then down in here this dollar and brackets means expand these variables. So you can see there I had some clever stuff going on to take all this lot and turn it into something that produces that same GCC command. Now this compiler is specified from up here and so on. And in fact, you can get even more complicated. Here is another way to do it where you tell it that you want the object files and that you need to build the object files by using the -c flag, as I showed you previously. So you can do all these things here. You can make files fairly complicated and get them to do some fairly sophisticated things. And here's the make file when you've got two files, for example, main.c and random.c. It goes through here and it can work out what it needs to do to compile those files. So if you've got 3 or 4, you can just start listing them along here and it's going to handle that automation for you. Now, as projects increase in size, so can the make files. Once you add in cross-platform options and other flags, what you're building, what you're including, what debug builds and release builds and builds that got certain things built into them, then they can get more complicated. The Makefile for the Linux kernel is over 2,000 lines long, and that's just the top level one. Then each of the sub parts of the kernel also have more Makefiles in them. So we need a way to automate the creation of Makefiles so that Make can automate the compiling of the source code. So this is kind of a second layer of automation. So GCC will compile the source code, Make will automate that, and now we need something that can automate the creation of the Makefiles. And this is where CMake fits in. I like to think of it as create Make or create Makefile, but actually the C in CMake stands for cross-platform, and we'll talk more about that in a minute. So CMake uses a configuration file called CMakeLists.txt. TXT, easy to edit in any text editor. Now the lifetime when you use CMake is that you define your project in the CMakeLists.txt file, you run CMake to create the Makefile, and then you build your project using the Makefile that has been automatically created. You then develop your code, you add code, you fix things, and you just jump around to using Make all the time. Once you've got that Makefile created, you can fix your code, you can add to your code, you just keep running Make and develop your code as you normally would. But if you add a new C file or a new header, or you've got a new dependency on a new library, then you'd go back up to step A, where you'd add in those dependencies, add in that new source code, you'd create the Makefile again, and then you'd carry on going that way. So you stay inside that loop just doing the Make and then edit the code until you change the structure of your project, and then you need to go back up to step A. Now CMake uses a thing called out of source build. Now traditionally Makefiles are placed in the same directory as the source code. So you go into the source directory where your hello world is, for example, and then you just run Make in that directory. However, CMake is different. The Makefile is generated in a different directory, can be a subdirectory, can be a directory somewhere else. And the CMake list.txt file is in the same source directory, but the automatically generated files are in a separate directory so as not to overwhelm your source directory. So your source directory remains pure, here's my source, and the build system remains somewhere else separate, particularly since also it's auto-generated. Generally your source code will be hand-generated by you, and you want this auto-generated stuff somewhere else. So the way it works like this, if I've got hello world, I might have hello world.c, I'll have this CMake lists file that we talked about, and then I might have a directory, a subdirectory called build. And if I go into build, I will then run CMake ... because I'm in the build directory. ... means in the directory above, which in this case means it picks up CMake lists in this level. And then that will create a whole bunch of files. Most importantly, it creates a Makefile, but also it creates some other stuff that CMake uses. And then if I run Make in that directory, then I'll get hello world binary in the build directory. So there we go. My hello world source code is in this upper directory. The CMakeLists.txt file is there, and then everything else happens inside the build directory. Now this is what a CMakeLists file looks like. This is the bare minimum. Hello W is our project. Hello W and hello W.c. You can understand here how this is going to be used. This is going to be the binary that's created by GCC. This is going to be the source code you need to add, and it will go ahead and create that Makefile for us. Okay, so as you can see, we have the hello world.c file, and we have CMakeList.txt. Let's just have a look at that, and there you go, just those 3 lines. So now what we can do is we make a directory called build. So remember, this is out of source tree, so we want to have a separate directory. Go into build. Obviously there's nothing in there at the moment, and now we do CMake ... CMake and use the CMake.list file from the directory above. That's what ... means, the directory above. That will go ahead and work out its stuff, and as you can see here now, there's a whole bunch of files, and there's no binary in there, but there is a Makefile, and if we look at it, it's pretty long and complicated because it doesn't matter. The complexity is completely hidden from us. We don't care. We just care that we can now type Make, and it has done, and there we can see hello world binary, so we can just run that like that, hello world. So now we use CMake to create the Makefile, and then we built it using the Makefile. Now you can do more complicated things. This is really absolute beginner stuff. So again, you've got this minimum required version listed here. You define the project as main, and here we've got 3 source files mentioned: main.c, random.c, and random.h. These are all dependent on each other, and they all come together to build main. And also I'm saying, well, I need the maths library, so there we go. Add the m minus lm, if you remember from the GCC command, add that into the mix as well, and it will take that and go away and create the Makefile that we need to build that project. Okay, so we've got our main.c, random.c, random.h, which is the header file for random.c. I haven't shown that, so let's just have a look at what's in there. It just defines that one function that we need. And of course, we've got our CMakeList file. And now if you notice here, it's got in add executable, you've got main.c and random.c and random.h. Okay, so let's go ahead and create a build directory. Okay, we go into the build directory. Of course, it's empty. Okay, and now we do CMake ... It will go ahead and do its stuff. So now it's created the files that it needs. Most importantly, we've got a Makefile. We can run make now. It will go ahead and do the thing. We can see there is now a main file in there. So now we can just go ahead and run main, and there we go and get those random numbers. So we did the same thing now, but using CMake to generate the Makefile, and then the Makefile to build the system. Of course, these Makefiles come with other things built into them, like make clean. That's all there as well. So it knows how to do a make clean, which means you can then do a make again. And it's also important to notice that the Makefile has all the right dependencies built into it. So if we go ahead and edit the random.h file, which of course is in the directory above, because we're now in the build directory. Okay, and we're just going to delete a few lines, but the point is that file has now changed. That file is different to what it was before. If we now run make again, the make has been built in such a way that it knows that if any of the source files get changed, you need to recompile. And it knows even about the header files like random.h. So as you can see, it's gone ahead and rebuilt that. And so although the program runs exactly the same, it knew to recompile. And that's, of course, an important part of make and CMake, the dependencies that when a file changes, the right things get compiled so you can carry on. Now, the real beauty of CMake is revealed when you understand that it can generate build files for other build systems, not just make. So this is where I was talking about cross-platform, because here we're talking about Visual Studio. You can notice that here. So that's Windows. Xcode, that's for the Mac. Ninja is a separate build system, an alternative build system that you can run on Linux. And the same CMakeLists.txt file can generate build files for other systems. This means that you can generate files from the same thing, and that's where the real power, this cross-platform power, comes from, because you need one CMake file and yet you can build this in a variety of different places. So let's just quickly talk about Ninja, because that's the other example I'm going to give you. Ninja is yet another build system. It takes an input that is the interdependency of files. It's build.ninja. That's really the equivalent of Makefile, and it orchestrates the building of them. But the key thing is here quickly. Its distinguishing goal is that it's fast. It's born from work on the Chromium web browser, which has over 30,000 source files. And other build systems like Make can take up to 10 seconds before it even starts to make the file, even before it starts compiling, because it's running around trying to work out what's changed, what needs to be compiled, what's the order of work that needs to be done here. Now Ninja can do the same thing on Chromium in under a second. So Ninja is meant to replace Make, and it's designed to have its input files generated by a higher level build system like CMake. So the Ninja.build files can be more complicated, but that doesn't matter because CMake is actually really kind of designed to create them. So if we have now Ninja as our build system, well, we've got our hello world C file, we've got CMake list.txt. That's our old Makefile directory. Well, we can have another directory now called Ninja. If we go into there and run CMake -G for generator Ninja ... means it picks up this one. That will go ahead and create some files, including build.ninja. And then if you run Ninja inside that directory, we'll then get the hello world binary built. So this is a different build system, different files, but still created from that same CMakeList.txt file. So looking here, we've got the old build directory we were just using. We've got CMake lists and we've got the source file. Let's create a directory called Ninja. Let's go into Ninja. And now, rather than just doing CMake ... we're going to do -G for generator. What generator? We want to use Ninja generator, and ... for the one above. And that's going to go ahead. And now in the Ninja directory here, we've got a whole bunch of stuff, including, most importantly, build.ninja. So now we can just run Ninja, and it will go ahead and build that. And as we can see here, we've got hello world binary there, and we can run that hello world. So if we go up a directory, the important thing is here we've now got a build directory and we've got a Ninja directory, and one's using Make and one using Ninja, but our source file, hello world.c, and our CMake list are untouched. So there you go, we've got two different build systems coming out now from CMake. So in summary, source code is compiled into a binary using a compiler like GCC. Make is a build system for projects with many source files. Ninja is an alternative to Make, and there are others. CMake is a build system builder. CMake generates make files or Ninja build files, as I've shown you. And CMake can also generate Visual Studio project files and Xcode files. Okay, so there you have it, my absolute beginner's guide to CMake. I hope you found it useful. Do let me know in the comments below if you use CMake. Is it your go-to tool, or is it something new you just found out now? Love to know where you are on that journey. If you like this video, please do give it a thumbs up. And if you like these kind of videos, why not stick around by subscribing to the channel? Okay, that's it. I'll see you in the next one.